Our next unit is going to be on rotation. And in this lesson, we're going to do a little introduction to rotational motion. And then we're going to look at linear versus angular measurements, and we'll look at angular velocity and angular acceleration. So two types of things we've seen a little bit before, dealing with velocity and acceleration, but this time instead of talking about in straight lines, or we'll be talking about it in terms of spinning or rotating objects. So let's take a look at this. So in this section, we'll be talking about the rotation of a rigid object around a fixed axis. And so we're talking about basically things that spin or rotate. So like a top that rotates, or like, say, picking up a 2x4, and as you turn, the 2x4 rotates around an axis. And so that's basically our overall type of topic here. And so let's define a couple terms here. So we said it's a rigid object, number one, and around a fixed axis, number two. So when we say rigid object, what we basically mean is an object that doesn't deform. Imagine that you had, like, let's say, a very long, thin branch. And so, if the branch basically, goes out here, you hold it like right about here and you try to rotate this, what you'll find happens is as you rotate it, the branch will sort of bend backwards. And that's what natural objects tend to do. And so that's not a rigid object in that case. So a rigid object is one that doesn't deform whenever a force is applied to it. And so that's what we're talking about. We're talking about a rigid object. You think of it more like if you had like a steel pole and you tried rotating a steel pole, you would not expect it to deform a whole lot. There wouldn't be a whole lot of lag on the end. In reality, if you really, really get down detail on things, is that all real objects deform to some degree. There's at least a little bit of deformation there when there's a force applied. We can treat solid objects or many solid objects as approximated as rigid if it takes a very large force to deform them noticeably. So, while as we said, that long branch is that you could whip that around and the end would sort of bend backwards as you turn with it. But if you had a very short stick, maybe one just 3 or 4 inches long, as you turn that, you wouldn't notice really any deformation as you rotated it. Or if you were to take a baseball bat, is that it's not a noticeable deformation whenever you rotate with the baseball bat. We can approximate that as being a rigid object, and that's what we'll look at here. We're going to assume all objects are rigid, which is reasonable as long as it takes a large force to deform them noticeably. So that's our first part here. Next part is, it says, around a fixed axis. And so the question is, what do we mean by a fixed axis? So let's suppose that what we're going to do is we're going to rotate something. And so here, let's say, is our circle of rotation here, and we're going to rotate this around some axis here. And so that axis might be down like that. And so we're rotating about this axis. And so when we say a fixed axis, basically what we mean is that this axis does not change location and it doesn't change direction. Is that it's possible, especially like you think about a top, as a top spins, the axis actually goes a little bit in circles. It precesses is the term that's used. And so the axis right now might be facing this way, but at some later point, the axis might be going, on like that, and so now the circle is going to be about like this as it rotates around. We're not going to deal with that green situation. We're going to assume that basically the axis stays in place. It does not change direction. It does not change location, and so as a result, it is fixed. So it's a fixed axis. And so that means we won't have to deal with things like precession, like we talked about, where the top spins as it goes around. Not just spins, but it also tends to have the axis moves around in a circle as well. The top of the top, if you have if we have just a top that looks a little bit like this, is that there's the top part that's right up there, and so this piece right here will actually tend to rotate around in addition to the overall top spinning. And we're not going to worry about that for here. That's what happens if you don't have a fixed axis. But we're going to keep things simple by saying, hey, we have a fixed axis, no precession, no wobbling or things like that. That goes beyond the scope of what we're going to talk about in this lesson. So let's talk about these ideas. So when a rigid body rotates about a fixed axis, every particle in the body moves around a circular path perpendicular to that axis. And so, as we sort of showed in our picture before, is let's say here is our, direction of our spinning object here. It's going to rotate in this direction. We have our axis that it rotates about, which is going to come down through here, is that axis is perpendicular to basically this this circle. You know, if we were to draw out a radius across that, we'd find that, you know, the axis is perpendicular to the direction of rotation. And so if we pick any spot, any point on this spinning disk right here, or in whatever spinning object is, we know we pick some spot right here, what we'll find is that there is a circular path that goes around this. And of course, I'm drawing it over an angle. If we drew it from the top side, you know, where it would look a little bit like this, and our axis is now, you know, going out of the screen or into the screen, is no matter what point we pick. And so if I pick some point that's right here, it's going to travel in a circular path around that axis. If I pick a point that's right here, it's going to travel in a circular path around that axis. And so no matter what point I pick, it's always going to travel in a circular path, which is perpendicular, as we sort of showed back over here, to the axis, and a circular path around the axis. This type of motion is called rotational motion, or sometimes angular motion. We'll probably use the angular term a little more commonly, because sometimes when people talk about rotation, they can get rotational motion confused with circular motion, which we talked about before. You know, circular motion is where you have a single object that travels around a curved path that goes around some point on a radius here. In this case, we're not talking about an object going in a curved path. We're talking about basically some object that is actually spinning or rotating. And so, you know, if we had like some object here that was rotating about this path like that, that's what we're talking about. We're talking about rotational or angular motion, not so much about an individual object that's basically moving along a curved path, even though individual particles in a rotating object, in one that's doing rotational or angular motion, are traveling circular paths. Since we're treating this as one object that's spinning as opposed to one object that's traveling on a circular path, that's going to be the distinction between angular motion or rotational motion and circular motion, which we discussed earlier here. And then we can also distinguish this from what's called translational or linear motion, which is what we've been talking about sort of at the very beginning of the year, dealing with velocity and acceleration in straight lines. And so that's what we kick off here. So let's go a little more into detail on this, on how we go about making measurements. So when we're analyzing angular motion, it's generally best practice to measure the angle an object rotates through in radians and not degrees. Everything we've done so far about angles has always been in degrees, you know. So we have, you know, some sector, and we have some angle theta that's in here, and we've always said, hey, we'll measure that in however many degrees that is. Well, this is a situation where it makes more sense to use radians. It'll make the math a little simpler than use degrees. And the reason why is because when we're talking about angular measurements, it's important to basically get the ratio between the radius and the arc length. And so, you know, we can see this picture I've got down in the lower right, where we have some angle theta. We have some distance d that goes around the arc that you can see that's right down here. And so that distance right there is d. We have some radius that goes along here, r, and some angle theta. Well, if we're talking about this in terms of degrees, we'd have to go through some process to basically figure out the relationship between that radius and that distance and that angle. But with radians, we can do this pretty easily. And so the reason why is because a radian, some of you know this from math, and so you don't have to worry about this, but just for those of you who need a little refresher, a radian is a unit of angular measure that's equal to 57.3 degrees. That seems a little arbitrary, but it's important because that's 180 divided by pi degrees. And so why do we care that it's 180 divided by pi? Still, it seems somewhat arbitrary. Well, the reason why is, you know, if you take a normal circle, you know, a circle has 360 degrees all the way around it. But, you know, if you were to take the circumference of that circle, and the ratio between the circumference and the diameter is 2 pi. And so, you know, your circumference is equal to 2 pi r. Well, the way that basically that radians work is radians say, hey, instead of just talking about a circumference, let's just call that a distance. Right here. That's the distance around the circle in this case. And that's going to be equal to this 2 pi, which is going to be our angle theta times the radius. And so because the fact that 1 radian is equal to 180 over pi degrees, you know, if we think about, you know, doing the math here, if we say, okay, 360 degrees, well, 360 degrees divided by 180 over pi, you know, 360 divided by 180 is 2. And then the pi is going to flip at the top, and so we end up getting that 360 degrees equals 2 pi radians. And so the same way that we get a 2 pi right here, that corresponds to the radian measure of going all the way around the circle. Now if we had a half circle, You know, instead of talking about going the full circumference, if we talked about doing, hey, let's do a half circumference right around here. Well, we'd expect that since the whole circumference is 2 pi r, then the half circumference would be just pi r. And that would be consistent with our idea about this, the relationship between the distance around and the angle in radians, because, hey, if we're going halfway around, if 360 degrees is equal to 2 pi, you know, that's what we said, 360 degrees is equal to 2 pi radians, then 180 degrees, halfway around the circle, would just be equal to pi radians. And so in our equation here, we'd say the distance is equal to r theta, where theta is our angle in radians. So in this case, our angle would be pi times r right here is equal to our distance of halfway around the circle. And so we get the distance equal to pi r, which is consistent with saying, hey, halfway around the circle should be half of 2 pi r, so it would just be pi r. And so this ends up being a very useful way to figure out the relationship between arc length and radius and angle, is that so if you have any sector of a circle here, and we have some distance that's around that, that's basically an arc length in there, if we know the angle in radians and we know the radius of the circle, then we basically say that the distance of the arc length, that part right there, is equal to the radius times the angle in radians. And so that gives us a very quick way to go back and forth between linear distances around the side of a circle and angular distances, you know, I'm sort of using quotation marks on that, air quotes, angular measurements of how far you go around the circle. And this works not just if you have just a single circle, this could work if you had many rotations. You could talk about something that's doing maybe like 50 radians, which would be more than one rotation, and you could figure out how far around the circle you'd have to go, the total distance you'd go around to spin around multiple times. And so this would be useful in a case where, you know, you have an object that rotates many, many times, and you're trying to find, hey, if I know how many times it spins, can I figure out how far an object, say, on the edge goes? And so this would let us communicate and translate back and forth between those two. So let's first look at angular velocity. This is the first of our angular measurements. Physically, angular velocity, which is given by the Greek letter omega, this is a lowercase omega right here, uppercase omega you may have seen before, it's the horseshoe, symbol for ohms in electrical work right here, it's the last letter of the Greek alphabet, but the lowercase omega looks like a W with a curved bottom, and so, you know, a regular English W would look like this, but an omega has sort of a curved bottom of each of the two little dips that are right in here, but that's omega, that's our symbol for angular velocity. But physically, angular velocity is a measure of how fast an object is rotating, and its units are radians per second. And so if you have an object that has a high angular velocity, it would have a large number of radians per second. If it had a low angular velocity, it'd have a low number of radians per second. And so if you had just omega was equal to 1, you know, so if we just said that omega is equal to 1, the unit would be radians per second. Symbol for radians is rad. So 1 radian per second, we said a radian is about 57 degrees, and so this would be an object that rotates through 57.3 degrees every second. And so that would be an example. If you had something that had an omega of 2 pi radians per second, then it would rotate once every second. And so that actually connects something here, because, you know, we can relate omega, the angular velocity, how fast something is rotating, to the frequency. Remember, we said before, frequency is the number of rotations per second, right? Well, one rotation is 2 pi radians, and so then we can sort of write out a nice little relation between angular velocity and frequency, that the angular velocity is equal to 2 pi f, where f is the frequency, in hertz. And so, as we talked about before, so H-E-R-T-Z, hertz, right there. And so that's our unit of frequency, and as we said, angular velocity is going to be in units of radians per second, right there. And so that's a way we go back between those two. Another one that's sometimes useful is the period. The period, remember, is the time for a single rotation. So if I have something that rotates 5 times in a second, then I would say its period would be 0.2, 1/5, because if it rotates 5 times a second, then it's 1/5 of a second for each rotation, and so that's the period. The frequency then, and that'd be 5 hertz, because there are 5 rotations a second. And so then if I wanted to find the angular velocity of that, I'd say, okay, let's see, omega is equal to 2 pi times the frequency. We said the frequency was 5 hertz right there, and so then omega would be just equal to 10 pi radians per second. And then the relationship between omega and the period is that omega is equal to 2 pi over t. And so, we could take this and reverse this around a little bit. We said that the period in this particular case, where something rotates 5 times a second, should be 0.2 seconds. And so we can verify that with this. We'll say omega is equal to 2 pi over the period. And so let's say we don't know what the period is right here, but omega is 10 pi right there equals 2 pi over t. And so we're going to multiply the t up on both sides, cancels t over here, divide both sides by 10 pi. So over here, divide this by 10 pi. Well, the pi's cancel out. We get 2 divided by 10. 2 divided by 10 is 0.2. And so we get a period of 0.2 seconds, which is what we expected in that case. And so we can see sort of the relationship between period, frequency, and then angular velocity, which is our main focus in this lesson. So let's try to get some equations on this. How can we calculate angular velocity if we don't know the period or we don't know the frequency? So, going back to our linear measurements, we said that linear velocity of a non-accelerating object tells us, how fast it's going. It's described as linear motion. And so that equation is our good old classic v is equal to d over t. Works great whenever things are not accelerating. The velocity in meters per second is equal to the displacement in meters divided by the time in seconds. All right, so that one's pretty straightforward. Now the angular velocity, however, omega of an object describes how fast an object rotates, and it's given by this equation. Omega is equal to theta over t, where omega, as we said before, is our angular velocity right there. Theta is going to be our angle that it rotates through, and that's going to be in radians, okay, because that's being radians here, and t is going to be our time in seconds, okay? And so that's going to be our basic idea on how this works. So if we had an example of, let's say you have an object that spins 10 times in 3 seconds. All right, so it does 10 rotations in 3 seconds. And so in this case, we say 10 rotations and 3 seconds. And we want to find, hey, what's the angular velocity? Well, 10 rotations, we know that every rotation is a full circle, right? That's going to be an angle of 2 pi radians, okay? And so if we go 10 rotations and then each rotation is 2 pi radians, that would mean that our theta in that case would be equal to just 20 pi radians right there. The time is 3 seconds. And so with those two, we can go ahead and figure out omega. Is that our angular velocity then, omega, would be equal to the angle theta, which we figured out was 20 pi radians, divided by the time, which is 3 seconds. And then it's a matter of just going ahead and doing the math on those right there, so that it comes out as what, 6.67 pi radians per second or something along those lines. It's generally best when you're doing calculations to leave the pi in here instead of multiplying it out. But once you get to your final answer, you do want to go ahead and do the math so that you can round up the correct number of significant figures. But in the middle of a problem, usually it's best just to leave the pi in its Greek pi form rather than inserting 3.14159, etc. In for it there. So just a little bit of advice in working these out. So that's angular velocity. Let's look a little more in detail at this and saying, hey, what if I need to convert between angular velocity and linear velocity? Like, let's say that I have, let's say a rake right here, and I'm going to spin the rake about this axis right here. I'm going to swing it around, and so it's going to be rotating about this axis point that's right here. And I know my angular velocity. Let's say that my angular velocity is 2 radians per second. And let's say the rake is 2 meters long. And I want to know, hey, how fast are the tines moving at the end? What is their linear velocity that goes right here? Well, that's pretty easy to figure out, because all we really have to do is go back and look at our original distance-angle relation that we said that, for some object, if you're moving around a circle, if you go some angle theta, and that means you're going to travel some distance d right here with some radius r, that the distance d is equal to the radius times the degrees, or not the degrees, sorry, the angle in radians, So let's actually apply this, because what we know is we know that the velocity of a linear case is distance over time. Well, we know that omega is theta over time, angle over time. Well, let's just look at this distance equation right here, the velocity equals distance over time, and say, hey, we know that the d equals r theta. And so we can really almost replace that d with an r theta right here. And we do that, we say, hey, wait a minute. Velocity then is equal to theta over t times r, because it's r times theta up here. We can pull that r out. But wait, what's theta over t? Well, theta over t is omega. And so we can say that the velocity, the linear velocity, is equal to omega times r, that the angular velocity times the radius is equal to the linear velocity. And that's our next little equation that's right here. That's a good, very quick way to relate these two. And so in the case of our rake out here, we say, hey, how fast the time's going? Well, we say the linear velocity is equal to the angular velocity, which was 2 radians per second, times the radius, which was 2 meters. And so in this case, we have a linear velocity of 4 meters per second is the speed of the tines of the rake as they travel outward like this. And so pretty quick, pretty straightforward in terms of being able to convert between the two. So let's go ahead and work out a problem. So what is the angular velocity of an object that spins at 200 RPM? RPM is shorthand, means revolutions per minute, and so so that's basically what that is right there. And so we say 200 RPM is the same as saying 200 revolutions per minute. All right, so let's see what we can get here. Well, we know that every revolution is a full circle, which is equal to 2 pi radians. And so that means that, our theta that we have here, the angle this goes through is going to be 200 times 2 pi. The number of revolutions in this time, which was a minute, times the number of radians in one of those, and so 200 times 2 pi. And so that means we've gone through an angle in this minute of 400 pi radians. All right, well, we know now what our angle is. We also know that our omega, our angular velocity, is equal to theta over time, the angle over the time. And so then we can say, all right, let's figure this out. So we know that our theta, our angle, is 400 pi radians. The time is revolutions, 200 revolutions per minute, and so we want to get this in seconds for our time, and so we'd say a minute is 60 seconds. And so now it's just a matter of doing the math. Now we can go ahead and get rid of that pi and move it into just decimal form. And so 400 times pi divided by 60 is, let's see, 20.94395. 4395 is what I'm getting, and that's once again units of radians per second. And so significant figure-wise, it looks like we just have one sig fig. The 200 is going to round to 1, and so we get an omega of 20 radians per second would be our final angular velocity here. All right, so then it's going 200 revolutions per minute. It's going at an angular velocity of 20 radians per second. So next, what is the linear velocity of a particle 0.3 meters from the center of the above rotating object? All right, so we want to find how fast the object's going. Well, our relationship between these two is that the linear velocity is equal to the angular velocity times the radius. And so in this case, we don't know exactly the shape of the object, but we do know the radius is 0.30 meters right there. We know that the angular velocity that's in here is 20 radians per second. Okay, so we have that right there. And so we should be able to find linear velocity pretty straightforwardly. And so that's going to be our angular velocity, which I'm going to go ahead and use the unrounded because we are in the middle of the problem in doing it this way. So 20.94395 radians per second times the radius, which is 0.3 meters. Radiuses should be in meters, but honestly, if it wasn't in meters, then it would just come out like if I use feet here instead. The velocity would come out in feet per second instead of meters per second, but here we want to have meters per second. But multiply these out, so 20.94395 times 0.3, I get 6.28 for our velocity. So 6.28 meters per second, because our unit of distance was in meters. And then sig fig wise, let's see, the 0.30 has 2, but then our original answer, the radians per second, our omega, had 1 sig fig, so that's going to round this to 1 sig fig. And so our final velocity is just going to be 6 meters per second for this particle that's 0.30 meters from the center of our rotating object. And so that would be examples of how you might go ahead using angular velocity to solve some problems. So next one we're going to look at then is angular acceleration. And so if we have an object that is rotating, but it's either speeding up its rotation rate or it's slowing down. You know, you could think about an example of something that speeds up its rotation rate, like if you basically take a ball and you spin it on your fingers, like a basketball that's spinning on a finger like that. So whenever that happens is the basketball starts off with zero rotation, but by hitting the basketball and trying to spin it is that we're basically increasing its rotation rate. So it would have a positive angular acceleration. On the other side of things, you can imagine, we'll have a problem a little later on like this, but a ceiling fan. You know, when the ceiling fan's been going, you turn off the ceiling fan, it takes some time for it to slow down to a stop. And so in that case, it has a negative angular acceleration. It's changing its rotation rate by getting slower in that case. It works sort of the same way as regular linear acceleration does. Whenever the rotation rate, the angular velocity increases, the acceleration is positive. When the angular velocity decreases, the angular acceleration is negative. And so the symbol for angular acceleration is the Greek letter alpha. And so the first letter of the Greek alphabet, it's similar to an A. It just sort of looks more like that rather than the standard A like this or like like that, however you do it here. But that's our alpha right there. That's the symbol for angular acceleration, whereas lowercase a is linear acceleration. Units of angular acceleration, as it says up here, are radians per second squared. Just like if you remember, linear acceleration is meters per second squared. And so instead of a distance on top, we have radians, an angle on top, because it's an angular acceleration rather than a linear acceleration. So, as we said, the acceleration of the rotation rate works the same way as linear acceleration, but instead of using the original and final linear velocities in time of the acceleration, the angular acceleration is determined by the original and final angular velocities in the time. And so if we look at this and try to compare them, our linear acceleration equation was a equals vf minus vo over t. The acceleration equals the final velocity minus the original velocity divided by the time between those two. So that's the one we've been using all year. But if we look at the angular acceleration equation, it's very, very similar. Instead of having linear acceleration, we have angular acceleration, alpha. Instead of having the final velocity in linear velocity, we have the final angular velocity. Instead of having the original linear velocity, we have the original angular velocity. And the time is still the time. And so that's our angular acceleration equation here. So alpha is the angular acceleration. It's in units of radians per second squared, as we said. Omega, F, is the final angular velocity of the object. So whenever it's stopped increasing or decreasing its rotation rate, what is its angular velocity at that point? That's in radians per second. Omega naught is the original angular velocity, so how fast it was spinning, what its angular velocity was at the beginning of the acceleration period, and that's also in radians per second, and of course t, which is going to be in time in seconds. And so that's basically it. And so it's pretty straightforward because it works exactly the same way as a linear acceleration problem. It just uses, instead of velocity final and a velocity original, it uses angular velocity final and angular velocity original, and you end up getting the angular acceleration. So what though if we have to use sort of our final of our kinematics equations? If I have to find how far something has traveled if it's accelerating, I use my linear d equals 1/2 at squared plus vot plus do. That classic one that we've been using all year right here. But what if I want to know the angle something is rotated through if it has an angular acceleration? Well, it works sort of the same way. Instead of having a linear distance, I would have my angle theta. Then it's equal to 1/2, instead of the acceleration a, we have the linear acceleration alpha. The t squared is the same. Plus, instead of the original velocity, I have the original angular velocity times t. Plus, instead of the original distance, I have the theta, the original angle that something is at whenever it starts rotating. And that would be used in a case where we say, hey, I've got some object right here that's going to start at this angle right here, and so that's the original theta. That would be your theta naught right there. is that angle. And we're going to accelerate it, give it an angular acceleration of some value for some amount of time, and then where does it end up is the reason why we have that theta naught that's right there. That's what that means. But you notice it works exactly the same as a linear equation, as a linear distance equation. It's just finding angle instead. And so, it's really one of these things that, we have our linear components, we have our angular components, is where linear has distance, angular has theta, right there, where linear has velocity, angular has angular velocity, and where linear has acceleration, angular has angular acceleration. They're really, they're analogs of one another. And the equations that they're in basically are, very, very similar to one another because they're just analogs. And so this last equation, the angular equation, theta equals 1/2 alpha t squared plus omega ot plus theta o, is going to work the same way as the linear one does. It's just with angles and angular acceleration and angular velocity, and not with distance and acceleration and velocity, sort of the regular old types we've been using. So now let's talk about how do we convert between these, between the linear and the angular forms. We've already seen a couple of these. Okay, well, displacement is that the linear displacement is equal to the radius times theta. That's the connection between those two. And then we said velocity, that the linear velocity is equal to the angular velocity times the radius right there. A little different order I put them in, but they mean the same thing. For acceleration, the linear acceleration is equal to the angular acceleration times the radius. It's always the same thing, it's what we said is, looking at our linear and at our angular. We said, from linear is that we have distance and velocity and acceleration. Angular, you have theta, the angle it goes through, and omega, the angular acceleration, and alpha, omega is the angular velocity, and alpha, the angular acceleration. And if you want to basically figure out to make these equal, not just analogs, all you do is you multiply all the angular values by the radius. And so if you have some object that's rotating around, has some radius that's out here, and this object is accelerating as it goes here, and you say, hey, what's the acceleration here? Find the angular acceleration, multiply it by the radius, that'll give you the linear acceleration. If you say, hey, how fast is it going at this point? What is its linear velocity? Then figure out the angular velocity at that point, multiply it by the radius, that gives you the velocity here. If you say, hey, it started off right here, and it's gone this far right here, and I want to know what is that distance that it goes right there. You find that angle theta, you multiply it by the radius, and that gives you the distance that it goes in a linear sense. And so it's very, very simply related. It's just a matter of making sure you keep track of all your sort of new angular quantities as opposed to the linear quantities. But this method sort of works out pretty well here. So let's see if we can do some problems on this. So let's say a fan spinning 2 times a second is turned off. If it takes 45 seconds for the fan blades to stop, what is the angular acceleration of the fan blades while stopping? And so, in doing this, let's figure out first. It tells us it's spinning 2 times a second. That's not radians. We like radians. And so if it spins 2 times a second, that's 2 revolutions. And each revolution, we said, is going to be 2 pi radians. And so we'll do 2 revolutions times 2 pi. And so that means that the original said the original velocity, the original angular velocity we're going to have here is going to be equal to 2 times a second. So that's 2 times 2 pi. It's going 4 pi radians in a single second. And so that right there would tell us that our original omega, our original angular velocity, is just going to be 4 pi radians per second. And so because of the fact that, it goes 2 revolutions, each revolution is 2 pi radians, and so 4 pi radians in a single second. So we have our original omega. That's actually omega O, because that's what it starts at. Well, what's our omega F? It's our final angular velocity. Well, the fan is turned off. Well, it says it takes 45 seconds for the fan blades to stop. If it is stopped, they're not rotating. If they're not rotating, then it's 0 radians per second is our final angular velocity. And so what we can do is we can now say, hey, let's look at our angular acceleration equation. So angular acceleration is omega F minus, that's not a plus, that should be a minus, omega F minus omega O over the time. And so alpha is equal to omega F, which we found was 4 pi radians, minus the original velocity, the angular velocity, which is 0, divided by the time, which is, we said, 45 seconds. And so it should just be 4 pi. So alpha is just going to be 4 pi divided by 45, and so alpha ends up being negative, sorry, what did I do wrong here? I got things backwards. Should have had someone here to correct me here. All right, we got those things mixed up here. Is that the omega f is 0 and omega o is 4 pi. Wow, because it starts off going 4 pi radians per second, as we said right here. It ends up going 0 right here. I got things backwards. Then just make sure it makes sense, because in this case the fan is slowing down, which means we should have a negative angular acceleration. And so that's how we caught it here. And so if that ever happens, that's how you know how to fix it here. 0 minus 4 pi is negative 4 pi over 45. And so that ends up being negative 0.27925. 27925 radians per second squared, because it's angular acceleration. Sig fig wise, the 2 times per second, that's infinite sig figs. 45 seconds, the only other value here, that's 2 sig figs, so we end up with an angular acceleration of negative 0.28 radians per second squared. All right, so that would be our final answer for this one right here. Next question. How many rotations do the fan blades make while stopping? Total rotations. Well, if we're looking for that, we're interested in basically what angle did it rotate through, which we'd find in radians. We can always convert back to rotations later. And since this is, if it wasn't accelerating, if this were spinning at a constant rate, we could just use that our omega equals theta over r, or theta over t. But they are accelerating, and since they're accelerating, then we're going to have to use our longer one. Our theta equals 1/2 alpha t squared plus omega o t plus theta o. All right, so in doing this here, we're looking for how many rotations the fan blade made. That's theta. That's what we want to find. Equals 1/2 times alpha. Alpha is our negative point. We're going to use the unrounded again. 27925 times the time, which is 45 seconds, squared, plus the original velocity of these fan blades. The original velocity of the fan blades we found was 4 pi radians per second. So times 4 pi times the time, which is 45 seconds, plus the original theta, which in this case, it doesn't really matter what it is. It doesn't ask us what the absolute location of the rotation, just how much it rotated. So we're comparing it from the original, and the original we'll say is 0 radians right here. And so in the process of doing this, let's see, so 1/2 times negative 0.27925 times 45 squared plus 4 times pi times 45 plus 0, and that ends up being that theta ends up coming out to be 282.74 radians. But the question asks how many rotations. Well, 1 rotation is how many radians? 2 pi. So we'll just take this and divide it by 2 pi. And that will give us the number of rotations. And so when we do that, is that it ends up being right out about 45. Actually, it's 45 right on the nose. So 45 rotations. And so that would be our final answer here, because we still have 2 sig figs. And so it says 45 rotations. You may notice that we start off with 45 seconds. That was a little bit of a coincidence, and the reason why is because whenever we put this into our 1/2 at squared equation, since our angular acceleration was basically 4 pi over negative 4 pi over 45, we took the 4 pi times the 1/2, gave us 2 pi again. Since 2 pi is exactly 1 rotation, then in this particular case, we end up getting it where they cancel out, and we end up with the same number of rotations as we did seconds. But that's only because of the fact this was spinning at 2 revolutions per second and slowed down to 0. If this had slowed down not to 0, or it had sped up, or it hadn't been 2 revolutions per second, we would not have ended up with the same value for our seconds as we did for our rotations. It just turned out that way in this particular case. So, one last question dealing with angular acceleration. So let's see if we can get this to work. Because right now, our computer is not responding. So let me get this down. It's all erased. All right, so let's look at our next one here. So a baseball bat is swung, so the sweet spot where you want to hit the ball on the bat is 1.25 meters from the axis of rotation, which presumably would be the center of the bat, or at least somewhere about probably somewhere between his hands and his body. Or the bat is rotated about 450 degrees during the swing, which takes half a second, assuming even acceleration and deceleration times what's the top speed of the bat. So first thing, let's look at that 450 and see if that actually makes sense here. So if we have, so we have home plate, it's right here. We have our batter, if the pitcher is somewhere back over here, going to pitch the ball that direction, when the batter originally stands with the bat, the bat's actually going to be angled back this way. And so in the process of swinging that bat, the bat is going to rotate around here and is going to rotate back to a new position, which is going to be back around here, if you think about it. And so because it's originally on sort of the batter's shoulder, it's pointing somewhat towards the pitcher, a little bit more towards maybe, I guess, third base, and then it ends up being swung so that it's back a little farther. So there's more than one complete swing here. And so what we're saying is that this whole angle around the whole thing is 450 degrees. But the question's asking about what's the top speed of the bat, and this bat doesn't travel at a constant velocity the whole time, because at this original distance where it starts at that original angle original angle which is right there, is that it starts off at 0. It has no angular velocity, and it's going to accelerate until it gets pretty much to this point right here. And at that point, then it's going to start decelerating because it has to come back to a stop by the time it gets to its second location where it ends up over here. And so really we have two segments here. We have a segment of acceleration going around here, and then we have a segment of deceleration that's going to come back around here. And so its maximum speed should be whenever it's located right across the plate. That's where we'd want our maximum speed to be, right there. And so that's what we're looking for. And so, it says that assuming even acceleration and deceleration times, and so that means that, it's going to be the same amount of time in both cases. And so really is that it tells us this time is half a second, but that's from bat stopped before the swing to bat stopped after the swing. Really to the point where we actually meet this right here, that the time for the swing is going to be half of our overall time. And so our time for this is going to be a quarter of a second right there. And so that's what we have here. Our angle is not going to be 450 because that's all the way around through the acceleration and the deceleration. It's going to be half of that angle, so that our theta is going to be 225 degrees right in here. And so we know that to sort of start this off. And so this is our initial setup. We do have an angle that's in degrees. We don't like that. We want to get that into radians. And so to get that into radians, we'll say, all right, so we have 225 degrees is the angle to our halfway to right across from when the bat starts to being right across the plate. We know that the conversion factor between those two is 180 over pi. And so this is the same as basically doing 225 times pi over 180. And so whenever you do the math out on that, let's see, 225 divided by 180 times pi ends up being 5 pi over 4 radians. All right, so that's going to be our theta right there. And so that's our theta. That's the angle the bat is swung through. And so that's our final one right there. Is this bat accelerating? Most definitely. It starts off sitting on a shoulder with an angular velocity of 0. It ends up, whenever we're done, with an angular velocity that's going to be high. So it's maximum right here. We're looking for that top speed right here. And so since it's accelerating, we're going to have to use our theta equals 1/2 alpha t squared plus omega O plus theta naught. And so our angle it swings through, we already know. 5 pi over 4 equals 1/2 times alpha, which we do not know the angular acceleration, times the time, which we do know because it takes half a second for the full swing. We're doing half the swing just from where it starts to getting across the plate, which is going to be 0.25 seconds. And then that's going to be squared because it's 1/2 alpha t squared plus the original velocity. Well, the original angular velocity of the bat, omega naught, is 0. It's sitting on his shoulder right there. And then times the time squared, which doesn't really matter. I'll put it in anyway. So 0.25 plus the original angle. We really aren't really concerned about that because we know it's going to change by 5 pi over 4, so we're going to go ahead and put 0 in for that, just like we do oftentimes on the distance one. And so getting this out, we have 5 pi over 4 is equal to 1/2 alpha times 0.25 squared, right there. So we're going to divide both sides by 1/2 times 0.25 squared. So divided by 1/2 times 0.25 squared right here. And so when we do that, we get a value of alpha is equal to 125.6637. So 125.6637061, and that's radians per second. All right, so we have our angular acceleration. We're not quite there yet because we want to find the speed. And so what we can use now is we can go ahead and say, all right, well, we know that angular acceleration is equal to omega f minus omega naught over t. And well, the angular acceleration we just figured out, 125.6637 equals omega f. That's what we're looking for, at least to start with. What the angular velocity is when the bat crosses the plate, minus the original angular velocity, which is 0 because it's sitting on the shoulder, divided by the time, which is 0.25 seconds. All right, so we should be able to multiply both sides by 0.25, and in doing that, that will give us omega f. And so multiply by 125.6637061 times 0.25 equals 31.4159.2654. I won't put them in here, but that's going to be radians per second. All right, so now we have the angular velocity at the point that's right up here, at the point where the bat crosses the plate. But we're asked about the top speed. That's a linear velocity. And so for the linear velocity, we'll have to find what's the relationship between these two. Well, linear velocity is equal to omega times r. And so the linear velocity of the sweet spot of the bat should be the angular velocity, which is 31.4159 times the radius of the sweet spot. It tells us that the sweet spot is 1.25 meters from the axis of rotation. And so we'll put 1.25 meters right here. And so multiply those out. We get a velocity of 39.27. We multiply those meters per second. And so let's see, sig figs wise, let's see, 1.25 has 3 sig figs. We've normally said degrees are to the nearest degree, and so that would have 3 sig figs, half a second's unrounded, so it'll be 3 sig figs for our answer. And so our final velocity is 39.3 meters per second is the end of the bat. And if you convert that into miles per hour, that's about 88 miles per hour. And so the end of the bat at this point, the sweet spot of the bat, in this half a second swing, where it accelerates up to full speed, it gets the plate, decelerates back, and it travels at 450 degrees in the process here, would give us about a 90 mile an hour swing at that point here, which is, it's not unreasonable given the circumstances.